In this video, I want to share my favorite perspective on trigonometry and kind of review all the trigonometry that you might need for calculus, but hopefully in a way that means you don't have to memorize very much and just can understand a few basic concepts. I want to begin with the unit circle. Imagine I have a circle of radius 1, and I'm going to imagine a point on that circle starts on the positive x-axis and rotates around in a counterclockwise way. I will use theta to denote the angle here, and note that the fact that I'm starting from the positive x-axis and going counterclockwise, this is just a convention that we're all going to agree on so that we can talk about the same things when it comes to our trig definitions. And then I can create a right triangle by considering the vertical and horizontal components of my particular point. And now I've done the setup to define my trig functions. I'm going to define the horizontal and vertical components to be cosine of theta and sine of theta respectively. This is a definition of what I mean by cosine and sine of theta when I'm in the first quadrant. Now, for a right triangle, you might have previously used the word adjacent for being close to the angle, opposite, the opposite side away from the angle, and hypotenuse for the long side. And when doing this, had seen the definitions that sine is going to be the opposite over the hypotenuse and cosine is the adjacent over the hypotenuse. That's great, but for our purposes, when I'm talking about a unit circle, the hypotenuse is always 1. And this is going to mean that adjacent and opposite are cosine and sine, respectively. And as we allow the angle theta to increase, the sides of the triangle can either point in the positive directions with respect to the x and y axes going out from the origin, or along the negative directions. And so sine of theta and cos theta are sometimes positive and sometimes negative. Now, as for that angle of theta, in calculus, we pretty much always use radians for this. And the basic idea here is that if I imagine going the entire way around the circle, this is going to be called 2 pi radians. And this corresponds to the notion that the circumference of a circle is 2 pi times the radius. So if it's a unit circle, then it's just 2 pi times 1 or 2 pi. And so the reason I like radians so much is that my circumference is 2 pi and the angle is 2 pi, they exactly match. Or if I just take a portion of it, like for example, suppose I do a quarter of a circle, this is theta going to 2 pi divided by 4 or pi over 2, and then the arc length from that quarter circle also pi divided by 2. There's this correspondence when you use radians. And the consequence of this in calculus is that you avoid a bunch of weird stretching factors appearing. If you try to do things in degrees, you're gonna have all these 2 pi divided by 360 degree factors appearing. It's really nice when you use radians. But you do have to remember that if you're going to your calculator and typing anything in, please make sure you've got the radian button selected on your calculator for anything that we're doing in calculus. Now, one of the things that immediately we get from this definition of sine and cosine is our first trig identity. If I take a normal right triangle, I can just zoom on this one, call it sides A, B, and C, we have the Pythagorean theorem that a squared plus b squared equals c squared. So in our specific context, where we have cos and sine, I get that cos squared plus sine squared is the hypotenuse squared, or 1. This is the so-called Pythagorean trigonometric identity, and we use this one all the time in calculus. All right, next up, graphs. Remember how cosine of theta is thought of as the horizontal component? And so if I just record that horizontal component as I rotate along, then I just get the graph of cosine of theta. Playing it slowly, when theta is 0, cosine of theta is going to be 1. But then as I rotate around to pi over 2, that horizontal component shrinks down to 0. Rotating further to pi, it starts increasing, now in the negative direction, so I'll say the graph goes down to -1. Rotating to 3 pi over 2, it's going to go back to 0, and then finally stretches back out to 1 as you get around to 2 pi. Similarly, we can look at sine of theta, which is now plotting out the vertical component. As the point rotates around the circle, this is going to give the graph of sine. So the point is that you can always generate the sine and cosine graphs and answer questions like cosine of 3 pi over 2 just by knowing the unit circle. By the way, you'll notice that the two graphs look really similar to each other, just sort of shifted over. So indeed, this can be captured by another identity, such as cosine of theta is just sine of theta plus pi over 2. It's kind of like the sine of theta is playing catch up to the cosine of theta and just running a bit behind. And again, I don't memorize the formula, like where exactly does the pi over 2 go? Is it plus or minus? If you understand the unit circle and how to come up with the graphs, you can figure these out each time on your own. These are all sort of nice values of theta because, as we'll see, you can just compute cosine and sine of them and get really clear, exact answers. You don't have to put it into a calculator and get an approximation. Often people memorize a couple special triangles here, and I want to show you how to come up with it. So let's take a look at this particular triangle. And what I notice is the hypotenuse has length 1 as always, but I don't know what the other side is going to be. Let's just call it something generic like a. Pi over 4 is cutting things exactly in half, so I have to have this isosceles triangle here. By Pythagoras, a squared plus a squared is equal to 1. So 2a squared is equal to 1, and if I solve this, gives the value of a equal to 1 over root 2. And mostly because that's less cumbersome to say out loud, I actually drew this trick of similar triangles where I can always multiply a triangle by a stretching factor. So if I multiply this triangle by every side by a factor of root 2, it gives me 1, 1, root 2. So this is how I memorize this. This is the 1, 1, root 2 triangle. And that's fine, but be careful. If you actually were to put it on the unit circle has hypotenuse 1. And so I want to label the two different sides of it 1 over root 2, 1 over root 2. If I wanted to compute something like, for example, sine of pi over 4, thus I'd get 1 over root 2. Now, for reasons that I've never understood, a lot of high school teachers will look at this and say, you should rationalize the denominator. And by this, they mean they don't want that root 2, that irrational on the bottom. So they can multiply the top and the bottom by root 2, give the value of root 2 divided by 2. Okay, I think this is a little bit ridiculous. I don't see any reason why you should rationalize your denominators. And I think it's actually, in many cases in calculus, more transparent to leave it precisely like this. But you do you. Okay, we should also do pi over 6 and pi over 3 quickly here. I've got the pi over 6 triangle. Note that because one of the angles is pi over 6, the other one is pi over 2, that's the right angle, then that means that in that top corner it has to be the value of pi over 3 in order for the sum of the interior angles to add up to pi, or 180 degrees. So the pi over 6 and pi over 3 triangle will sort of do at the same time. Again, you can memorize a special triangle, but if you ever forget, there is a little trick here. In this case, what we're going to do is put the mirror image of this down. And what this means is now we've got pi over 3, pi over 3, pi over 3 appearing in each of the three corners. This is an equilateral triangle. So the right side of it has to be of length 1, split in half. This means half and a half. So now that I have this little trick, I can get rid of the bottom. And now just by Pythagoras, I'm going to get the value of root 3 divided by 2 going on the bottom. And again, since this maybe looks a little bit cumbersome, you could stretch this all out, multiply everything by 2. And I call this the 1, 2, root 3 triangle. It rolls off your tongue very nicely. By the way, in this video, I'm trying to prepare you for what is commonly taught in calculus. It's a very different question about should it be taught this way. So don't treat this video as me saying what I think calculus should be like, maybe just saying I'm trying to prepare you for how it is. Now, what can be a little bit trickier here is if I do some other weird value, like how about 11 pi over 6? So I kind of want to show you how to do all of those other ones. And basically, these are multiples of either pi over 3, pi over 4, or pi over 6. So this one I've chosen 11 pi over 6. And what I like to do first, if I'm working by hand, is try to figure out like which of the 4 quadrants is it sitting in. In this case, 11 pi over 6 is just pi over 6 less than 2 pi. That is, 11 pi over 6 counterclockwise is the same thing as pi over 6 clockwise. No matter which one you've chosen here, you're always going to be able to come and put in that special triangle with the pi over 6 at whatever location you've got it. And this means we already know its values. It's going to be a 1 and a half and a root 3 divided by 2. So let me suppose I was going to ask, I don't know, how about sine of 11 pi divided by 6? Well, sine was the vertical components, and according to this triangle, that's the value of 1/2. But notice crucially, my point here is in negative values of y. So I get from the special triangle the value of 1/2, but I have to adjudicate, is it positive or negative? And because I'm down here beneath the x-axis, the answer to this is now negative 1/2. So you can use that kind of trickery to figure out, at least for the special values, multiples of pi over 3, pi over 4, and pi over 6, what you're supposed to be doing. Okay, so we've mostly talked about sine and cosine, but there's other trig functions, as you likely know, tangent and cotangent, secant and cosecant. And basically, if you think about a triangle having the opposite adjacent and the hypotenuse, there's 6 ways you can take a ratio of one of those to one of the other ones. And each of those 6 ways is given a name. These sort of foundational principles, unfortunately, you just have to sort of memorize the name of which one associates to which. There's not really a shortcut there. However, for the other four, tan, cotangent, secant, and cosecant, I always like to have in my mind how they relate to the original sine and cosine. In calculus, this is really, really useful as we start taking derivatives of one of the other functions. So tangent, for example, in my mind is sine divided by cosine and so on. This is the way I typically try to have it memorized in my brain. Then if you have to figure out, I don't know, tan of 11 pi over 6, you just do sine of 11 pi over 6 and you do cosine of 11 pi over 6. You go from there. I can also come up with the graph of other trig functions, like for example, tangent. Here I've put in the graph of cosine and the graph of sine. And let me just overlay the graph of tangent. Tangent is this one that I've done here in the pink. And if you ever forget how to come up with the graph of tangent, here's the idea. We know that tangent is sine divided by cosine. So whenever cosine is 0, which you'll notice happens at pi over 2, 3 pi over 2, negative pi over 2, and so forth, any places where that denominator is 0, it has to have a vertical asymptote. So we have these spikes that are vertical asymptotes at pi over 2, negative pi over 2, and so forth. Then in the numerator, which is sine, well, sine, which is the blue graph, is 0 at 0, and pi, and 2 pi, and negative pi, and so forth. And so our graph of tangent has to be 0 through negative pi, 0, pi, 2 pi, and so forth. So knowing those anchors where the vertical asymptotes are, where the zeros are going to be, it's just a matter of connecting. Like, do they go up to positive infinity? Do they go down to negative infinity? And say in 0 to pi over 2, we know that it has to go to positive infinity because sine divided by cos in this region, the graph of cosine is positive, the graph of sine is positive, so the tangent has to be positive well. So I know that in this region, it's going to positive infinity. Whereas, for example, between pi over 2 and negative pi over 2, my sine is positive, my cosine is negative, so sine divided by cos better be negative, and that's why tangent starts at negative infinity and goes up to 0. You can do the same kind of analysis to come up with the graphs of secant, cosecant, whatever you like. And then now that we have these other trig functions, we can look back, for example, remember the old Pythagorean identity, sine squared plus cos squared equal to 1 that we saw earlier in the video? Well, I can get the analogs of this for the other trig functions. For example, I could divide both sides by sine squared. This would give me 1 plus, well, cos over sine is cotangent, and 1 over sine squared is going to be cosecant squared. And I get a second Pythagorean identity, this time relating cotangent and cosecant. Or if instead I prefer to divide by cosine squared, I get tan squared plus 1 equals secant squared. Now what happens a lot in calculus is that there's these 3 different pairings, sine and cosine, cotangent and cosecant, and tangent and secant, and they really often work together. And so what I do a lot of the time is take whatever complicated expressions I have, they're combining lots of things, and try to make them all be sines and coses, or all cotangent and cosecants, or all tangent and secants. These sort of 3 pairs will keep on working together. Now, you then might ask, well, hold on, don't those other trig functions mean something like geometrically? And indeed they do. I have my standard picture here with the particular theta, but what I can do is actually draw a bigger triangle. So this one on the base, it's going to have length 1. I'm going all the way out, and then I go straight up, and then I have this sort of now longer hypotenuse. Bigger triangle, what is cosine of this bigger triangle? Well, it's 1 divided by the hypotenuse. In other words, the hypotenuse is 1 over cosine, which was our definition of secant. So secant has a geometric meaning on the unit circle. If I go to the other side, try to take sine, right? Remember, sine is opposite over hypotenuse. We just decided the hypotenuse was going to be secant of theta. Secant of theta is 1 over cosine. So moving it to the other side, I've got sine divided by cosine. That's tangent. So the opposite here is going to be tangent. Now, I'll actually be honest, this sort of geometric meaning isn't something you're going to be using all the time in calculus. It's okay if you forget this geometric meaning precisely. Maybe the larger point is just to note that all these trig functions do have a nice geometric meaning, and from time to time that can be useful. All right, now we got to talk identity. There are so many identities out there, it can be really cumbersome, so I want to show you a nice path forward to learning the major trig identities. So I've actually put up only 6 out of the much larger selection that I think are most commonly found and used in calculus. Now, more important than memorizing, because indeed, you can always look it up unless your calculus professor is one that really wants you to memorize these for your tests. What's more important for solving homework problems is like knowing the general purpose behind the identities and recognizing that there's one that you should go and look up. So for example, the sum identities is an expression for any time that you're trying to take the sine of a sum or the cosine of a sum. And then the double angle ones are actually just a special case of that. They're useful and they come up in a lot of standard calculus problems, but really all they're doing is saying, well, what if I say that the two angles, the alpha and the beta, are both equal to theta and I get these results? And so anytime I see a sine 2 theta or a cos 2 theta, I know there's a formula here and I can go and look them up if I happen to have forgotten. At this point, they'd be drilled in my mind, and so I haven't forgotten them. And then the one that actually seems to be the most useful in calculus is these power reduction identities. Really, all they are is taking the double angle identity for cosine, rearranging it, and then maybe using it Pythagoras in the case of the cos squared. But they're useful in calculus because sometimes when you're trying to do some weird integral and you've got a higher power like cos squared, now you can reduce it to a lower power, something to do with cosine 2 theta, and that's often a little bit easier. So the point is that you can get a lot of these new identities from the old identities. You don't have to remember very much. But we still have the question, where does the first identity, those sum identities, actually come from? And there's actually a really nice little geometric proof of this coming from the unit circle. The idea is, let me imagine I rotated in amount alpha. And then let me imagine I then further rotated in amount beta. So my question now is asking if I want to know, for example, sine. I want to know what happens for sine of alpha plus beta. Where have I ended up if I do alpha first and beta second? And now I just sort of want you to tilt your head a little bit. I have formed this triangle here by dropping a perpendicular on the triangle that's got this angle of beta. And it's just the same kind of analysis we've done before, like the adjacent was going to be cosine, the opposite is sine when our hypotenuse is 1. So this is a similar triangle to what we've seen before, just sort of rotated around a little bit. Okay, now I'm going to go and look at the triangle on the bottom here. Again, it's a new one we haven't quite seen before. Instead of going all the way out to the edge of the circle, I'm just going to the spot that intersected that perpendicular from the first one. So I got a new triangle here. Now, if I want to look at the opposite side of this triangle, well, this actually, I can say, is just going to be, well, it's sine of the angle alpha, but there's a stretching factor. Since the hypotenuse is no longer length 1, the hypotenuse is cosine of beta, then that gives me my stretching factor, so it's sine alpha cos beta. And indeed, if I compute sine, it would be sine alpha cos beta divided by sine alpha, and sine alpha would be sine alpha. Okay, now here's the real insight. This triangle that I've highlighted here is a similar triangle, that means all its proportions are the same, to this one up here. And most importantly, what that means is that the angle alpha is the same. So I can do the same kind of thing if I want to come along here. Well, this is the adjacent for that weird, turned around triangle. And so what do I have? It's going to be the stretching factor of sine beta to represent the hypotenuse, and then it's the cosine of the angle alpha. Putting all this together, if I look at just what the vertical is on both sides, this is going to give me my double angle formula that sine alpha plus beta is sine alpha cos beta plus cos alpha sine beta. There I have my formula proven. Now, again, the geometric derivation here isn't necessarily the thing you're using all the time in calculus. What's more important is to note that all of these different identities, let's put the list back up again, all these different identities here don't come from nowhere. Like, there's a very nice geometric meaning for the first one. I'll leave it as an exercise for you all to figure out cosine of alpha plus beta. If you saw the sine one, you just gotta label different parts of that to be able to get to the cosine one. And then the other identities were just a little bit of algebra coming from there. So they're not completely magical. They have these really sort of nice geometric meanings, but nevertheless, if there's one list you sort of want to sort of be familiar with, this is at least my short list. Okay, so that was a lot of trigonometry facts, but hopefully I've given you sort of a speed run review or maybe sort of reframing of how you thought about trigonometry, and hopefully touched on most, probably not all, but most of the important facts about trigonometry that you're going to be able to use in calculus.